Hello everyone, I'm Guan Yu, and today I will be presenting my circuit and its design. A biomedical signal processing system optimized for hardware acquisition. Before diving into the schematic, it is essential to highlight why specialized biomedical signal processing is required. Human physiological signals naturally exist in microvolt or millivolt range. Because these biopotentials are exceptionally weak, they are easily affected by surrounding noise. Therefore, we must amplify these weak biological signals while simultaneously filtering out unwanted noise to ensure biosignals are properly acquired. Looking at the schematic, there are four distinct stages. I will begin by analyzing stage 1. This initial stage serves as our preamplifier. Its primary job is to extract the weak raw signal from our input, provide immediate voltage amplification, and suppress early stage noise before the signal degrades. When we observe the schematic, stage 1 is configured as a closed-loop, non-inverting operational amplifier. This is because the input signals enter by the positive input, and the feedback loop is connected to the negative input. In this operational amplifier, we intentionally utilize the TL072 IC, which is a dual JFET input operational amplifier. Its advantage includes high input impedance, low input bias current, and low noise performance. These advantages makes it suitable for capturing and amplifying weak physiological signals without accessing loading or distortion. Since this is a non-inverting amp, its formula for gain will be 1 plus RF over Rin, where R2 equals to RF and Rin is equals to R3. So we just sub in the values and we get 23 is the gain of the amplifier. Looking at the input path, the signal first passes through capacitor C1, which serves as an AC coupling capacitor, effectively blocking any unwanted DC bias voltages from entering the system. Simultaneously, the resistor network of R5 and R6 forms a voltage divider. This divider establishes a stable midpoint voltage, often referred to as a virtual ground, at exactly half of our voltage. This midpoint voltage allows our operational amplifier to operate with only a single power supply, preventing the negative halves of the Harvey waveform from clipping at 0 volts, by giving the waveform enough voltage headroom. Following the input stage, the negative feedback loop forms an active bandpass filter, which is a combination of high-pass and low-pass filter. A passband filter allows only a specific band of frequency to pass through. Any frequency that is outside of the specific range gets rejected. It is an active bandpass filter and not a passive one, because it uses an IC and it is not limited to resistors, capacitors only. Earlier, I mentioned that bandpass filter consists of both high-pass and low-pass filter. Let's identify them. There is a parallel arrangement of C2 and R2. This is actually our low-pass filter. That is because at low frequencies, C2 acts as an open circuit, which forces the feedback current entirely through R2 to achieve our maximum expected pass gain of 23. At high frequencies, C2 transitions into a short circuit. Current bypasses R2 and reduces our feedback impedance to 0, which drops the stage down to a safe unity gain of 1. Because when R2 is 0, the gain becomes 1. Conversely, the input of C3 and R3 forms our high-pass filter. At low frequencies, or DC, C3 acts as this breaks the path to ground through R3, creating an infinite impedance at the inverting input node, which mathematically attenuates the amplification down to unity gain. At high operating frequencies, C3 acts as a short circuit, allowing current to flow freely to ground, enabling us to get our full voltage gain of 23. Finally, we have capacitor C4, which serves two roles. First, it acts as a final AC coupling barrier to block any DC offset voltage accumulated, so the waveform does not get cut due to the voltage offset. Second, capacitor C4 also forms a secondary high-pass filter as the signal transitions to stage 2. Now, looking at the solution of the lab results, we can see that as the frequency increases until 100 Hz, the gain keeps increasing to 22.5. However, frequencies larger than 100 Hz causes the gain to drop. Based on the table, the decibel with the gain value closest to 23 is 24 decibels. Moving on to the graph, we can find the negative decibel threshold by subtracting 27 by 3 decibels to give us 24 decibels. From there, we can find the low cutoff frequency, which is 16 Hz, and high cutoff frequency at 1.2 kHz. By subtracting 16 Hz from 1.2 kHz, we get the bandwidth value of 1184 Hz. To set up TP1 and TP2, we must first set the supply voltage to 9 volts. Then, we set the function generator input to 200 mV for amplitude and 1000 Hz for frequency. And then we connect the red wire of function generator at the node of the positive side of the capacitor C1. Next, we connect probe 1 of the oscilloscope to TP1 and probe 2 to TP2. Once connected, we can observe two clean non-distorted waveforms. They are in phase with each other. They are in phase because the op-amp is non-inverting. Finally, we can see that the output voltage is actually 3.44 volts. Although the value is different from the one in lab solution, it is still within a reasonable range. Moving on to stage 2, this section of the system utilizes the same IC, but the different sections for configuration. Looking at the schematic, we can identify this stage as a closed-loop inverting amplifier configuration. This is because the conditioned signal from our previous stage passes through the input network and enters the inverting or negative terminal at pin 6. Because this is an inverting op-amp, the output waveform will experience a 180 degrees phase shift. The negative feedback loop features a 100 k ohms potentiometer, designated as P1. This variable resistor serves as our feedback resistor, RF, which works together with the input resistor R4. Consequently, the closed-loop voltage gain of this stage can be derived by negative half RF over Rin, where RF is P1 and Rin is R4. By manually turning the trimmer of the potentiometer, we can dynamically scale the value of RF, allowing us to adjust the circuit amplification. When the trimmer is turned to the max, whereby P1 is 100 k ohms, the gain will be 10. Using the formula, we will get negative value for the gain because the negative sign indicates that it is 180 degrees out of phase. To maintain single supply operation for this second stage, resistors 9, R9 and R10 form a dedicated voltage divider type between VCC and ground. In real-life context, based on my research, the inclusion of an adjustable gain stage is important for biomedical instrument design such as the heartbeat acquisition system because patients' biopotential varies. While one individual might produce a relatively strong, easily detectable heartbeat signal, another patient's biopotential may be heavily attenuated. Integrating this manual adjustment allows clinical operators to calibrate the system's sensitivity specifically to the patient, ensuring weak signals are adequately amplified for processing, while preventing over-amplification from driving the op-amp into saturation and distorting the diagnostic data. To set up TP2 and TP3, we connect probe 1 to TP2 and probe 2 to TP3. As you can see, when I turn the trimmer, it changes the waveform. As I adjust, we can observe that the waveform saturates at a certain point. After finalizing my adjustment, you can see the output voltage starts to saturate at around 6.40 volts. In the third stage, looking at the operational amplifier configuration, it is a second-order Sallen-Key active low-pass filter. It is made out of two low-pass resistor capacitor networks. R7 is paired with C7 and R8 is paired with C6. Together, they allow low-frequency signals to pass through while attenuating high-frequency noise. In this configuration, capacitor C7 provides a feedback path that shapes the frequency response near the edge of the passband. Looking closely at the surrounding components of this stage, the signal first passes through an AC coupling capacitor, C5, which isolates the stage by blocking any accumulated DC offsets from the previous stage, while allowing AC signals to pass. Simultaneously, resistors R11 and R12 form a local voltage divider connected to the non-inverting input. Lastly, there is capacitor C8, which also acts as a AC coupling capacitor to filter any DC offsets. Before diving into the calculations, it is crucial to analyze the clinical and practical significance of these voltage dividers. In traditional laboratory electronics, operational amplifiers typically demand split power supplies, such as positive and negative 15 volts, to process alternating currents that swing below zero. However, for portable wearable healthcare devices like a heart rate monitor, carrying bulky split power systems is highly impractical. Instead, our system is optimized for a single supply configuration. To process an alternating biopotential signal without losing data, we establish a stable reference point known as virtual ground at exactly half of our supply voltage using these resistor networks. By shifting our baseline signal up to this midpoint, we allow the negative half of the heartbeat waveform to have sufficient voltage headroom, preventing it from clipping against the 0-volt ground rail. This design drastically simplifies our power distribution circuitry while preserving the integrity of our data. Now, let's look at the calculations. To find the color frequency, by this formula, and we get 996 Hz when rounded off to the nearest whole number. Just to add on, usually we can use the formula 1 divided by 2 pi fc, but in this case, since C7 is not equal to C6, the conditions to the shorter formula are not met, therefore we can't use it. By looking at the results of frequencies in relation to its gain, we can see that at the gain is 0.8 volts. Looking at the graph, since there is unity gain initially, the graph will start on 0 decibels. We can identify the negative 3 decibel threshold at negative 3 dB. And you can see that the high cutoff frequency is 1000 Hz. Hence, the bandwidth will be 1200 Hz, because 1200 minus 0 Hz equals to 1200 Hz. To set up TP3 and TP4, connect input signal and probe 1 together at TP3, then probe 2 at TP4. First, we set the function generator amplitude to 5 volts and frequency at 1k Hz. We can observe that Vin is 5.04 volts and Vout is 3.44 volts. When we calculate the gain using these values, gain is roughly 0.68, which is within a reasonable range of values compared to the lab solution. This justifies that the cutoff frequency is 996 Hz, as after 1000 Hz, the gain drops significantly. Finally, at the last stage, the configuration is actually an audio amplifier. It uses the IC LM386, which has a high current drive capability, allowing to deliver high current and power directly into a low impedance speaker load. In terms of performance when driving heavy current, it performs better than standard operational amplifiers because it does not clip the waveform or burn out. Hence, we use the IC LM386. Another perk of this IC is that it is designed to work in single supply mode, so a voltage divider is not needed. Before the input signal from the previous stage passes into the IC, the potentiometer of 100k ohms, a variable resistor, forms a variable voltage divider with the incoming signal. By physically turning P2, the user can alter the fraction of the signal voltage that passes into the IC input terminal. This allows them to turn down the speaker volume if the heartbeat clicks are too loud, or turn it up if the signal is faint. Next, capacitor C13 acts as AC coupling capacitor that filters out any DC bias voltage. This is crucial in an audio amplifier as DC bias voltage can cause physical damage to speakers. So it is important that the configuration makes sure no DC bias voltage passes to the speaker. Finally, we have C15 and R17 connected together to form a high-pass filter. C15 filters out frequencies that can cause unwanted violent vibration. To set up TP4 and TP5, we connect probe 1 to TP4 and probe 2 to TP5. This time, we place the function generator at the beginning of the circuit, at the positive side of C1. When I turn the trimmer, we can observe changes in the waveform, where the amplitude changes and the saturation is observed. After adjusting, we can see that 6.80 volts is the maximum peak-to-peak voltage obtainable before saturation.